Welcome to today's webinar on the evolution of OE wheel balancing standards and their impact on the aftermarket, presented by Hennessy. I'm Greg Smith with Modern Tire Dealer Magazine, and I'll be your moderator for today's event. I encourage you to ask questions during the webinar at any point, and we will try to address them all. However, if we do not get to yours, don't worry. You will be contacted by email with a response after the event. Our presenter today is Kevin Keefe, Vice President of Marketing at Hennessy. Kevin joined Hennessy over 13 years ago as a product manager. He previously worked at General Electric with several assignments in product marketing and Six Sigma. Over the years, he has held product development and technology roadmap responsibilities for both Coates and AAMCO wheel service equipment. He also has extensive practical experience in applying lean manufacturing principles such as 5S, standard work, and variation reduction to drive quality and productivity in high-volume retail tire service operations. Now, I'll hand it over to Kevin.
Thanks, Greg. First, let's just take a quick look at what we're going to cover today. First of all, we're going to look at kind of an overview of trends in OE wheel balancing, what's happening with OE wheel balancing tolerances, and some of the really big changes that have been made to factory balancing systems and tolerances. Also, we've all heard a lot about rolling resistance and the pursuit of low rolling resistance tires. We want to talk a little bit about what that means to you as a tire dealer and how it will impact your operation. Also, we'll look at further impacts to aftermarket wheel balancing practices, kind of back to the fundamentals. There are going to be some challenges we're going to talk about, and it really comes around to doing the fundamentals really well. And so we're going to talk a bit about mounting errors, residual imbalance, machine calibration, and wheel weight usage, all of which really drive about 85% of the opportunities to get it right the first time. Then we'll pull it all together real quick and leave some time for Q&A. So let's start with OE wheel balancing trends. Historical OE wheel balancing tolerances have been fairly forgiving over the years, with about 3/8 of an ounce of static and about 3/4 of an ounce of dynamic residual imbalance being acceptable for most manufacturers. But fast forward to today, and we're starting to see several import nameplates tightening their balancing specs, especially for allowable dynamic residuals. So 0.18 ounces down from 0.75 ounces is an order of magnitude change, and also is well below today's aftermarket specs of 1/4 to about 0.3 ounces in aftermarket machines. With those changes, we're also starting to see U.S. vehicle manufacturers make some substantive changes in the way they balance tires and wheels in their factory and the specs to which they balance them too. So here's a good example. One vehicle manufacturer has begun transitioning its balancing process and has actually replaced the human element with a highly accurate robotic measurement and application system. And in this process, most of the clip weights have been largely replaced by a large reel, kind of hundreds of pounds of adhesive weight that gets automatically fed into a robotic balancing system. And that weight is then cut to 1/100th of an ounce accuracy, so tremendous level of accuracy. That weight segment that's accurately cut is then fed into a robotic application tool, which then places it with pinpoint accuracy on the wheel in the right spot. The result is a wheel assembly that's got virtually no leftover on balance. So that's quite a different story than what we've typically seen when vehicles hit a dealership lot. The plan for this manufacturer is to spread this technology across their platforms, except where they have insufficient plane separation. So basically what that means is most alloy wheels from this manufacturer will be balanced to these tolerances. Steel wheels still present a challenge from a plane separation mode, so they'll be balanced conventionally. So why all the changes? Well, mostly what we're seeing is vehicle design trends are evolving in the face of CAFE standards. Those are corporate average fuel economy standards that have been set forth by our government. And the results have been lighter vehicle design, stiffer suspension systems, and higher inflation pressures, all of which kind of drive vibration sensitivity. We also commonly hear of what we've dubbed the SUV effect, which is when the motorist drives their four-door sedan all week, then jumps in their pickup on Saturday to pull the boat to the lake, and they say, hey, this doesn't ride like my car, and they perceive that they've got a ride quality problem. And that's really exploded with the popularity in light trucks and SUVs. Also, we've got the coming impact of reduced rolling resistance, which we'll discuss in more detail. All in all, vehicles just continue to become more sensitive to vibration. And in order to maintain customer satisfaction, the aftermarket is really going to need to determine how to achieve tighter balancing tolerances. So here's what's going on from rolling resistance perspective. And based on the latest information we have from tire manufacturers, we know that their engineers are pursuing the least possible tire mass. And the way they're getting there is through reduced tread thickness, which leads to reduced tread life, and higher inflation pressures, both of which will drive vibration issues. In order to compensate for the reduced tread thickness, we're seeing tire diameter start to creep up as well, which can also lead to vibration because the farther away from the wheel center of gravity a given unbalance gets, the greater the vibration it will cause. And then they're also pursuing the least possible dampening of the tire and wheel assembly, the least possible deformation of the tire, and the least possible deflection of the tire, which means those systems will absorb less and less vibration and less road noise. So it's going to be very necessary to do things a little bit differently to avoid this compounding effect of ride quality challenges that, frankly, we're already facing in the aftermarket. So now that we know what's coming down the pike in terms of ride management challenges, it's a good idea to step back and really understand the fundamentals of balancing, as well as the most common causes of balancing errors in the shop. We all know why to balance wheels. You talk about it to your customers every day. But given the evolution of vehicle and tire designs, aftermarket service providers will really need to pay more attention to the details in order to maintain customer satisfaction and loyalty. So let's start with a quick overview of balance and unbalance. So at its most basic level, a wheel is balanced when its mass is distributed equally around its axis of rotation, so it rotates without any vibration. However, if an excess of mass exists on one side of the wheel, which creates an unbalanced condition, the centrifugal forces acting on the heavy side will exceed that of the light side and pull the entire wheel in the direction of the heavy side, resulting in a vibration. Let's talk about the types of unbalance. And we'll start with dynamic imbalance. Virtually every tire and wheel you see in your shops presents with dynamic unbalance. And dynamic imbalance is the sum of two different types of unbalance, static and couple. A static unbalance exists when the principal axis of inertia is displaced parallel to the wheel's axis of rotation. So this is what's often described as a hop. That's a sensation that customers will feel from an assembly that's got static unbalance. Conversely, a couple unbalance exists when the axis of inertia intersects the wheel's axis at its center of gravity, and you've got two equal unbalanced masses 180 degrees apart. And this type of unbalance will cause a wobble or a shimmy sensation. And you'll see why that's important as we move through kind of some of the common causes of balancing errors. So let's talk about those, and we really want to talk in detail about the top four. But an understanding of the basics of balance and unbalance provides the required backdrop for putting together an effective plan for managing these challenges in your shop. And based on our field experience with thousands of shops, we found that getting back to actively managing the fundamentals of the balancing process in your shop is really the best strategy for avoiding problems and comebacks. The good news is if you just pay close attention to the top four causes of vibration-related comebacks, you'll address about 85% of the problems. And as we start to see more of these vehicle designs and tire designs enter the aftermarket, this will become even more critical. So the first topic in mounting errors is static mounting error. In this case, a wheel is mounted off its true center, perpendicular to the balancer shaft. And this is a very common occurrence that can cause big problems. In fact, just a 10,000th static mounting error on a 16-inch, 40-pound tire will generate a vibration about equal to that of nearly an ounce of static unbalance. And that's going to bring a lot of vehicles back for rework. And just to give you some perspective, 10,000ths of an inch is about the thickness of a business card. So that's the level of accuracy of centering required to produce a good result. And there are a lot of ways, and they're very common, to generate a static mounting error. The first is nicked cones. So just a very shallow nick in a cone. If the wheel happens to settle into it during the mounting process on the balancer, you're going to generate a static mounting error. Also cones with worn IDs or worn balancer shafts. Also improper clamping, and this could be caused by a weak balancer spring, whether it's captured or loose. And also using steep cones, which are a little more challenging to get heavy wheels up on and centered versus shallow cones. And I've seen it dozens of times. A shop will get frustrated with comebacks and rework, and they'll purchase a new wheel balancer, and the problems go away, which is great. But what happens in many cases is that the shop spends $7,000 or so for a new set of mounting adapters that really would have solved the problem in the first place. There are also dynamic mounting errors, and dynamic mounting errors on the balancer is when the wheel is actually offset from the balancer's faceplate. And this type of mounting error can be caused by dirt on the faceplate, surface imperfections in the wheel, a bent center disc, or a problem that I see all the time, and it's really, really preventable just through enforcing good balancing practices, and that's front coning OE steel wheels. The way OE steel wheels are stamped, they're stamped from the backside. That's the only reliable mounting surface. The perception among a lot of techs is that front coning is faster, and I'll grant that on the first tire and wheel assembly out of 4, it's a little faster, but it's slower on all the rest. And the potential for mounting errors and rework from front coning OE wheels is a very common but very preventable cause. So what else can you do about mounting errors? You can pay some close attention to your mounting adapters and replace them at various intervals. For cones and shafts, we highly recommend replacing those at 30,000 cycles or 3 years. And your spring, again, whether it's captured in the balancer's faceplate or loose, we recommend replacing that every 10,000 cycles or 1 year. That spring is really the critical component that provides the clamping pressure necessary to make sure that that tire and wheel assembly centers up on your balancing adapter. So at the end of the day, a few $100s every few years will keep your wheel balancer delivering like new results a lot longer than you might think. That said, the wheels on some vehicles simply do not respond well to conventional mounting adapters. For example, if you think about 2011 and up, GMC Sierras, Yukons, Chevy Silverados and Suburbans, also late model Ford E350 and F350s, those all we found require specialty mounting adapters such as stud plates and offset adapters to get the job done right. And we're constantly releasing those types of adapters. So if you've got a problem with a particular vehicle, make sure you check with your coast distributor, one of our district managers. We've likely got a really cost-effective solution. So to kind of tie up mounting errors, when you get back to the shop today, I'd urge you to take a look at the condition of your balancing adapters, take stock of your balancing practices, and talk to your techs about problem vehicles. Everybody's shop demographic is going to be a little different. Everybody's vehicle demographic is going to be a little different. So you don't need to invest in everything, but there's probably a few key adapters based on your shop profile that you're going to want to have. And at the end of the day, a little attention and investment here is going to pay big, big dividends for you in preventing comebacks and rework. So let's move on to residual unbalance and why that's important. So we're going to look at some of the causes of residual imbalance first, but with the advent of computer balancers, dynamic balancing became commonplace. However, due to the quarter-ounce round-offs and the propensity for operators to make slight weight placement errors, conventional dynamic balancers can oftentimes leave an excessive residual static unbalance, leftover static unbalance that results in a ride disturbance complaint.
While we have a break for a second, Kevin, a question came in. Is residual unbalance a new problem? This individual had never heard of it before.
It's not a new problem. It's always, residual unbalance has always been in the background of every balancing spend that you do in the aftermarket. And different balancers have different tolerances for what is allowable. And we'll talk about that, the specifics of that in a minute. But at the end of the day, you know, there's been enough room in those tolerances today so that you can make a few mistakes and not kind of cross that threshold of residual unbalance that'll drive a comeback in a lot of vehicles. But what these changes that we're talking about in terms of vehicle design and in terms of tire design, specifically related to rolling resistance, you know, that window is going to close just to maintain parity with the results that you've been able to give your customers day to day. So residual unbalance has always been there. It's always been behind the zeros if you put your balancer into fine mode. Our contention is, based on the facts that we know today, it's going to become a bigger issue, and we're going to have to really pay attention to a few key things like preventing mounting errors, residual unbalance, balancer calibration, and wheel weight usage to get rid of the top root causes of unnecessary residual unbalance.
Kevin, so that you can just catch your breath for a second, I would like to remind everybody we are getting good questions being sent to us, but we do encourage you to ask any and all questions that you have during the course of this webinar, and time permitting, we'll try to address them all. And of course, if we don't get to them during the webinar, we will contact you by email with a response after the event. Now that I've let you take a sip of water, Kevin, we'll go back to you.
Thanks, Greg. So let's take a look at what causes excess residual static unbalance. So as I mentioned earlier, wheel balancers typically operate with a quarter-ounce blind. Some balancers actually operate with a 0.3-ounce blind. So that means the balancer is going to show you zeros up to and including the scenario where the actual residual or leftover unbalance is 0.24 ounces all the way up to 0.29 ounces in either plane. So you'd see this value by taking your balancer out of round-off mode. That process is a little bit different for every balancer, but it's fairly easy to do. In the best case scenario, as we've depicted here, these small residual imbalances are exactly 180 degrees apart on opposite sides, and they statically cancel each other out. And this condition does not result in an excess residual imbalance problem. However, take those same unbalances and put them completely in phase, as we've shown in this slide, then they're completely additive. And the result can be around 1/2 ounce up to 0.6 ounces of leftover static unbalance. And by OE standards, that's going to bring a lot of vehicles back. So how can you prevent problems from residual imbalance? Well, the first thing you can do, and the best thing you can do really, is to conduct kind of a final quality check for leftover static unbalance. And the process will, again, vary depending on your particular balancer, but you know, kind of absent any specific instruction based on your balancer manufacturer, what you do is put the balancer in static mode, and you correct that residual imbalance by placing an adhesive weight in the center plane of the wheel at the indicated position. And this will take care of the static unbalance that's left over, but it also ensures that you don't induce any additional couple unbalance, which again will drive a comeback. Several Coates machines will show you both dynamic and static values, so there's no need to toggle back and forth, and it's kind of a built-in quality check that doesn't require any additional navigation or button pushes. Again, recall that virtually every motor vehicle wheel suffers from dynamic unbalance, which is a combination of static and couple. I would highly encourage you, if you've got a balancer equipped with a weight saving mode, to turn it off. Weight savings balancers intentionally leave a couple unbalanced of a known magnitude, up to 1.5 ounces or more depending on the wheel. The manufacturers state that the threshold for this residual unbalance is calculated such that the leftover couple won't cause a ride vibration complaint. But that's, as we'll see as we move forward, is a little bit of a slippery slope. So to understand what a weight savings balance does, I'm going to draw an analogy to something those of you who have been in the business long enough will remember: bubble balancing. So back in the day when vehicle wheel assemblies were balanced with a bubble balancer, you would basically get a static balance. And if the operator knew what he was doing, he could do it in such a way that he wouldn't induce any additional couple unbalance, but there would always be a couple unbalance left, assuming that he could statically balance it perfectly. The weight savings balancer will do virtually the same thing. It will balance it statically, and it will leave a couple unbalance of a known magnitude. So that's basically the difference. Bubble balancer would give you a couple unbalance left over, but you wouldn't know how bad. And frankly, yep.
Kevin, we got a very interesting question that just came in. Are you saying that as OEs change their residual unbalance specs, that my weight savings balancer will actually increase my chances of comebacks?
I'll say yes, and then I'll explain why. So a weight-saving balancer's main operational goal is to attempt to lower wheel weight consumption. And the way they accomplish the savings is basically by instructing the technician to apply less corrective weight than is necessary to balance the wheel. So in the scenarios where the conditions of that tire and wheel would lend itself to a weight savings balance, that wheel is not balanced and has residual unbalance. So the only way to save weight when balancing a wheel is to accept residual unbalance as the cost. And if you agree that residual unbalance is going to become a bigger and bigger issue in light of what we know about vehicle and tire designs, then that's a long way to say yes. It's going to become a bigger and bigger issue if you're using weight savings balancing modes as these vehicles start to hit the aftermarket. Okay. Given the increasing importance of managing residual imbalance, Coates launched the Vero Series V200 direct drive wheel balancer last spring with ProBalance technology. And ProBalance technology was developed to minimize both static and couple imbalances simultaneously with no trade-offs or switching between balancing modes. Knowing what we know about the vehicles coming down the pike and the tire designs coming down the pike, this really gives us the ultimate solution to handle residual imbalance without any additional time or operator effort. So you can talk to your authorized Coates distributor or one of our district managers if you'd like more information on that balancer. All right, let's leave residual imbalance and head into balancer calibration. And it's important to know the distinction between two different types of systems, of dynamic sections. And so we'll talk about the most common first. The spindles of most wheel balancers in the market today are driven indirectly by belts and pulleys, which are in turn driven by a fairly small motor. And because of all these interconnections, this design is plagued with noise and vibration caused by variable and changing conditions in the system as a result of worn belts or pulleys or changes in temperature and humidity. And because of all this noise and the fact that this noise changes over time, zero, in other words balanced, is a floating value in an indirect drive balancer. And you have to calibrate, and you have to do it often to establish and reestablish that zero value. So with an indirect drive balancer, depending on how often you calibrate, zeros on an indirect drive balancer's display don't always mean balanced. And that's a risk and a trap that a lot of folks aren't aware of. That zero is always based on what the current level of noise in the system is. And it's an artificial zero. So again, as things change, as you get belt wear, as your pulleys loosen up, as temperature warms up throughout the day in various climates, this becomes an issue, and you have to calibrate often. So on the flip side of that is our direct drive balancers. And Coates high volume wheel balancers feature a uniquely designed dynamic section, which is the section that reports vibration to the balancer. And in this design, the drive system integrates the balancer's motor and spindle into a single factory pre-balanced assembly with zero noise, no belts, no pulleys, no opportunities for wear. So that ensures that any signal or noise that's reported back to the balancer's processor is coming from whatever's hanging out on the end of that balancer shaft. And so zero always means balanced, and you never have to calibrate zero on a direct drive wheel balancer. So that takes away one big opportunity for error. So again, you never calibrate zero on a direct drive balancer, and zero always means balanced no matter what. We have a depiction here of our direct drive system.
Kevin, this one just came in. Okay, it makes sense that a direct drive would deliver a better balance. Then why do companies still make the indirect drive units?
Frankly, my best guess at that is that there's a fairly significant design cost penalty that probably a lot of manufacturers aren't willing to pay for a direct drive system. But we feel that it's the best solution for making sure the job gets done right the first time, especially in light of these changes we know that are coming down the pike. Plus, there's something we haven't talked about is there's an added benefit of durability with direct drive systems. We've literally got hundreds of thousands of direct drive balancers in the field, and we only ship a handful of replacement motor assemblies each year. Very reliable. That's why we can warranty the direct drive system in our Vero balancers for 10 years. Also, we ran a oldest direct drive contest a couple of years ago, and the winner came from had a machine that came from actually the winner, and a second place entrant had machines that both came from our first week of production in the early 80s. The only thing they had really done was the optional electronics upgrades over the years, but they were still using direct drive balancers from the early 80s. So another testament to their durability. Okay, moving on, just a word of caution about calibration. Although indirect drive balancers, as we discussed, should be calibrated often. That means weekly or even daily, depending on your shop environment. Calibration should really be a last resort for weight chasing, which is kind of the common complaint, which many folks try and resolve with calibration. But there's a lot of other potential causes and fairly common causes of weight chasing. And only once you've eliminated those other potential causes should you move on to calibration. It's often the first reaction or the knee-jerk reaction to a weight chasing situation. But again, in all the work that we've done over the years in the field, we found that a large percentage of those complaints can be solved by paying attention to some of these other issues. Okay, moving on to wheel lid application. Short lining is an issue when it comes to potential comebacks and balancing accuracy. And so short lining is a term for a common strategy used in the aftermarket, which involves the use of just a few clip styles and adhesive weight. This practice could be used with reasonable success with lead wheel weights because they're malleable, and with a big enough hammer and a strong enough arm, they could be kind of forced to conform to multiple flange styles. However, unlike with their lead counterparts, lead-free weights are not malleable, nor are they forgiving when applied to flange styles for which they're not designed. When that happens, the result is sprung clips. In other words, the clips lose their spring tension, which is what keeps them on the wheel, and also poor fit, and both of which can lead to fall off. The fact that you should be wary of any lead-free wheelway proposal that relies on short lining, because it's a pretty good indication that the clip gaps have been relaxed, in that they will not likely perform to OE rim retention specs. Again, if you can't keep the wheel weight on the wheel, you're going to have a vibration issue. So the most successful conversions to lead-free weights that we've seen in terms of comeback avoidance and just general disruption to balancing processes have been those that have employed a full line of clip styles. That said, the alternative to that would be to increase your use of adhesive weights or some combination thereof. But either way, there are some very simple gauges that can sit at the balancer out there that make identifying the right clip style very fast, very easy, and don't require leafing through application charts or relying on some fairly simple color coding. So using the right weight for the wheel application is a very, very simple thing you can do to avoid a lot of problems. So pulling it all together, boy, it's only going to get harder to deliver the ride quality your customers expect, the ride quality they enjoy today. And in many cases, as we move forward, legacy balancing technologies and legacy balancing practices are going to struggle a bit to meet evolving OE specs, which like it or not, frankly, they're going to set the aftermarket benchmark. But as we have reviewed today, there are several low-cost and no-cost process improvements you can make today that will increase your odds of getting it done right the first time, which is what drives customer satisfaction. So again, just a quick review. Inspect your mounting adapters, replace them as needed. Very reasonable investment to keep your balancer running like new. If you've got some problem vehicles that you commonly see in your shop, invest in those specialty adapters that make sense. Pay attention to residual imbalance. Unfortunately, again, as balancer manufacturers have done a better and better job of delivering technology and features and really good user interfaces, we've made it just excessively easy to skip past some traps. And we've reversed some of those with some recent product launches, but you have to pay attention to residual imbalance even more so as we move forward. Again, weight savings modes are going to cause you more harm than good as we start to see these new vehicle designs come into the aftermarket. Make sure you maintain and regularly calibrate if you've got an indirect drive wheel balancer often. And very simple, use the right weight for the job. If you don't have the right weight, using an adhesive weight to get it done. And again, our representatives are available to help you implement any improvements that will drive shop profitability and customer loyalty. We're here to help. So thank you very much, and I'd like to take a little bit of time to answer some of the questions that are scrolling down my screen.
Well, Kevin, you certainly have piqued the audience's interest. We do have several different questions. I think the best way to do this is to start off. There were two different questions on a similar topic.
Okay.
You're going to the basics first. The question, and I'll give you both. The first question is, what is front coning? Okay. And the second part of the question is, I have a problem with my tech's front coning aluminum OE wheels. Is this as critical as steel wheels? Okay. So there you go, a two-parter.
Two-parter, okay. Well, front coning, and I'll describe this kind of in order of mounting to the balancer shaft. So think from the faceplate out to the right. So rear coning, which is the much preferred way of mounting a tire and wheel assembly on the balancer. You would start with your spring, unless it's captured, then it's already there. Then your cone, then your tire and wheel assembly, then your hub nut or your quick nut. So that's rear coning. Front coning would be start with your tire and wheel assembly, oftentimes no spring. I see that quite a bit. and then apply the cone next, and then attach the hub nut and apply the pressure on the cone, which is now seating on the core fascia of the wheel, if you will. So that's front coning. And again, the perception from a lot of techs is that it's faster. And I'll grant it's faster on the first wheel, but on a set of 4, I'll beat you every time doing rear coning, because on the next 3, you don't have to take the cone off. So, and the second part of the question was, I'm sorry.
I have a problem with my techs front coning aluminum OE wheels. Is this as critical as steel wheels?
It's not as critical because you've got a machine surface on an alloy wheel for a cone to seat on. But I'll make this caveat, is that we've seen a lot of wheel designs, even in OE, where it's been a little bit challenging to get through the various steps in the hub area of that wheel and actually get the mounting adapter, or the cone or the collet seated on the surface of the wheel that will actually seat back up on the vehicle hub. So you may not be as successful from the front as you once might have been. So although it's probably not as grave an error as front coning a steel wheel, I guess I could put it that way, I still wouldn't recommend it because of the complexities of the wheel geometries that we see, even in OE wheels in the last 5-6 years. Plus, you also have to be wary of the plastic-clad wheels. Never want to front coat one of those.
Moving forward, if you have a weight-saving balancer and turn that feature off, will the technician need to balance assembly in dynamic mode and then switch to static and check reading? If static is over 0.25 ounces, then you would place corrective weight to correct for a more accurate balance, was the question. If balancer is not direct drive, wouldn't you risk chasing weights more, since these balancers tend to need calibrated more often?
Okay, so I'll answer the first one to the best of my knowledge, because each of these machines operates a little bit differently. But if you were to take a machine that has the weight savings feature out of weight savings mode, it would, at least with the ones I've seen, operate like a conventional dynamic balancer, and thus, yes, you would have to toggle into static mode, determine if you've got an excess static problem, and correct for it with a single adhesive weight in the center plane of the wheel, so as not to induce any additional couple on balance. And that would obviously take care of the problem. Now, different vehicles have different tolerances for static unbalance, so I would stop short of saying a 1/4 ounce is the right threshold for every vehicle. Light trucks are obviously going to have a lot more forgiveness than some smaller sedans, but in practice, that's the right process, absolutely. And then in regards to indirect drive balancers, I like this question because it's going to illustrate the trap. Just because an indirect drive balancer is not calibrated doesn't necessarily mean it's going to chase weights. It may not be absolutely calibrated to 0. And what generally causes chasing weights is when your balancer, your position calibration comes out. So in other words, you've got an encoder in that balancer that reads the position of the wheel where it wants you to place the weight. And that can come out of calibration and cause you to place the weight in an area that the balancer doesn't expect it or doesn't want it, and that'll cause the weight chasing. The danger of not regularly calibrating your indirect drive to 0 is that you can be free of weight chasing. You can be balancing one spin every time, and if you haven't calibrated that 0, you don't know it's balanced. That's the trap in indirect drive balancers. Conversely, a direct drive balancer, let's take the very uncommon scenario where you lose position calibration on a direct drive balancer. It may take you 3 or 4 or 5 spins to get to 0. You chase it all around. But when you get to zero, it's balanced, it's done, it's good. It's not going to drive a comeback.
Okay, simple question. Is static balancing as good as dynamic?
Well, static is a component of dynamic balancing. So again, static is what we, rewind 30 years, to bubble balancers. That's what we were doing then, right? And for those vehicle designs back then, big heavy vehicles on stiff steel frames and lots of cushion and nice forgiving suspension systems, you didn't feel a lot of that residual imbalance. It didn't translate, and it didn't have a vibration path to the passenger compartment. But fast forward to today, and let's not even think about what's coming down the pike. Let's just think about what we're dealing with today. We've got unibody construction, stiffer suspensions, heavier tire and wheel assemblies, which just add unsprung weight to that suspension or to that vehicle that's not hung up by the suspension system. Static balancing is just not going to get you there. And frankly, even if set aside all this extra attention that we want you to pay to residual imbalance, if you just did what your balancer could do today in terms of dynamic balancing, it's not going to cost you any more time. It'll cost you maybe a little bit more in terms of wheel weights, but you're going to end up with a much better result and a much lower comeback ratio.
Kevin, the next question. What is an easy way to find out if our machine is direct or indirect in the manual on the machine?
Okay. I am going to go out on a limb and say, first of all, if it Coates, to our knowledge, is the only manufacturer of direct drive wheel balancers. And over the years, we've had a very broad product offering, but our high volume wheel balancers have always been direct drive, and far and away it's on the decals or on the serial tag. That's probably your best bet and the easiest way to figure it out. If not, I can almost guarantee it's going to be on the front cover of the ops manual.
The next question is going to challenge your technical knowledge a bit. You mentioned that there were several different ways to stop weight chasing besides calibrating the machine, but never said what they were. Can you explain this in
Sure.
detail?
Absolutely. As a matter of fact, here I'll put them back up on the screen and we can talk about them a little bit. So this graphic shows kind of the main drivers of weight chasing, the potential root causes of weight chasing. So what we see a lot of time are weight placement errors. So every operator is a different height, is depending on their form factor, maybe a little bit farther away from the wheel than others. And everybody sees top dead center a little bit differently. That's called parallax error, and we try to mitigate that by having laser-guided weight operation systems. But again, on older balancing systems where you don't have that luxury, that weight placement error is a very common cause of weight chasing. Also, and I've seen this a lot too, where they don't get the wheel positioned exactly at top dead center before they hammer the weight. And again, in a lot of new wheel balancing systems, there are stop and lock functionalities or position locking foot pedals that can be used to kind of grab that wheel and hold it at top dead center. And there's indicators on the balancer screens to tell you when you're there, but we see that a lot, quite a bit. And with the OE wheel designs really trending towards having a soft lip, requiring an adhesive weight balance, at least for the outer plane. Wheel balancers, even just from 6-7 years ago, a lot of times lack the systems to help the operator do a first time one spin taper weight placement, so that would result in a respin. Also, kind of there's the operator side, training, using the wrong wheel weights or clipped weights. They don't have the exact increment they need. So in a lead weight, they'll clip part of the end off, and obviously that's not accurate. Or conversely, they'll take two unequal, smaller weight increments to sum up to the weight that's being called for, and not center them properly. That'll drive weight chasing. There's also kind of tire and wheel issues, the wheel slipping on the faceplate, which could be the result of a worn hub nut or a spring that's lost its, the bouncing spring that's lost its tension, foreign material inside the tire. We see this all the time, especially with these flat repair substances in a can, and water even inside tires. We've seen that a lot. And the mounting errors that we've talked about can even lead to some weight chasing. And then, just because the knee-jerk reaction a lot of times is if I'm chasing weights, I'm going to calibrate. We see a lot of calibration errors. Folks who either aren't used to doing it or miss a step, and the last calibration is what causes you to chase weights. So there's a lot of things that can drive a weight chasing scenario other than the balancer being out of calibration. And if you just look for the really common ones that kind of we've noted here, and eliminate those before you go ahead and do a calibration yourself, or you call a service technician to execute a calibration, you'll be better off.
Okay, next question. Our machine does not have a spring to use with rear coning. Is it necessary to have this when rear coning?
Yeah, absolutely. And I'll just venture a guess and say it's been lost or misplaced, or maybe you've got a capture back spring that's just seized up. But you absolutely need a rear spring when you're back coning, and that's the way we want you to do it, because that provides the most reliable seating surface for that balancer adapter. So there are a couple bucks. I would pick up the phone when this webinar is over and order yourself one. You'll be amazed at the difference in results you'll see.
The next one's kind of self-serving, but we love it anyway. Great information. I sell equipment. Can I offer my clients a replay of this webcast at a later date?
Absolutely. I think it will be available both on Modern Tire Dealer, and the folks there have been gracious enough to allow us to host it as well. So you'll have a couple places to go see it, and I believe it's going to be out there several months, if I'm not mistaken.
And this is off topic from the presentation, but do you have any updates on state legislation or laws relative to wheel weight materials and restrictions per state?
I would assume that everybody's heard about Minnesota. That's the latest state to adopt lead-free wheel weight legislation. Unfortunately, the rate of change going from lead to lead-free has really slowed, and we've seen a lot of legislation come up in various states, Connecticut being one of them, and we've seen it in a few other states where it was actually voted down. And we're in, as an industry, and I'll really only speak on behalf of the industry, if I may, that we're in the place that we really never wanted to be, which is the market's at about half and half from a unit volume perspective. And so we've all invested in, at the risk of whining here, we've all invested in duplicative manufacturing processes for a lead-free offering, or sometimes two lead-free offerings, to serve a market that, from a piece perspective, really hasn't grown a heck of a lot in the last 10 years. So there's a little bit of irony in that. A lot of the pushback at the legislative level is, and rightfully so in some cases, is trying to protect the constituents from increased operational costs, right? But the irony of that is, until we can get to a point where we could shed some of these redundant manufacturing operations and focus on, geez, it'd be even great if we could just get out of lead and focus on one or two. Our cost structure as an industry changes. As a commodity, those cost savings get driven pretty quickly down to the end user. And without sitting here and doing all the math, I'm going to go out on a limb and say, net probably wouldn't be a big change in operational expenses. So, we had hoped that the EPA would drive this at a federal level. They took it up again. Geez, I don't know. probably more than a year or two ago,
Well,
with no action, and
okay.
so here we wait.
Well, very good. And of course, everyone can continue to look to Modern Tire Dealer or moderntiredealer.com as any states are trying to enact anything. We will post it on our website or in our magazine. We're fast running out of time, so I'm going to try to squeeze in 2 more questions. Do you recommend using finger plates on every assembly possible as opposed to cone and pressure cup?
That's a good question, actually. So if you're really looking to error-proof mounting tires and wheels on your balancer, there's kind of one way that you can use, one methodology you can use that'll guarantee a like 90% success. So start with your spring and your back cone, tire and wheel assembly, and a finger plate. So on OE wheels, which are hub-centric, what that finger plate will serve to do is exert the clamping force equally around the hub bore and replicate kind of the clamping force and the location of that clamping force when it goes back up on the vehicle. So it helps you replicate the way that wheel will mount when it goes back in the vehicle, which is exactly what you're going for when you mount the wheel on the balancer. You want to duplicate, replicate as close as possible that mounting scenario as it will be back in the vehicle. That's when you're going to get your best results. On an aftermarket wheel, which is lug-centric, when you cone it, because of the design of aftermarket wheels, those every SKU per se is designed to fit a kind of a wide variety of hub bores. You may or may not be rear coning on the surface that will do the final seating on the vehicle hub. So what the fingers enable you to do is kind of reassure that you're centered, and you're again exerting those clamping forces in the way that they'll be exerted when it gets back in the vehicle. So again, if you do everything in that fashion, spring, rear cone, this is assuming they don't require any specialty adapters like some of the vehicles we discussed, tire and wheel assembly, and some type of finger plate, then your hub nut, you're doing the best you can day to day to deliver the best results you can to your customers.
Is there a place to find imbalance specs for OE rims if I'm having a triple vehicle?
I'll tell you what, we've had to do a lot of research to find them. We've used our industry contacts and relationships to because they're kind of evolving even today as we move ahead. The dealer's going to be able to help you out a lot with that, and frankly, we've leaned heavily on a few local dealers to help us root cause and fix a lot of vibration issues with particular vehicles. So I would say start there. If you can't get the answer you're looking for, give us a shout or drop us an email, and we can hopefully shed some light.
Final question for you.
Yep.
Can you check a balancer for calibration before you calibrate the balancer?
Again, I'll qualify that. You can check it for position. On a direct drive balancer, you never have to check it for zero. It's always zero. But what you can do is a rotational check to make sure the position is good. The position calibration is good. So start with a wheel that's balanced as close to zero as you can in fine mode. You may want to use we use balancer putty. You can use something similar to get it down as close to zero in fine mode as possible. And then loosen the hub nut slightly, rotate that using your valve stem as kind of your index. Rotate it 90 degrees, retighten the hub nut, spin it again, and see how it reacts. As long as you're within a quarter ounce of where you were at your last readings, you're probably in pretty good shape. And you would do that all the way around the wheel. And that's a great way to check. Great way to check your calibration.
Well, very good. It's certainly been a very fast hour. But unfortunately, that's all the time we have for today. Now, for anyone who asked a question that wasn't answered, Kevin and his team will be following up via email to answer your questions individually. We hope that you all enjoyed today's webinar, I want to thank Kevin, Keith, and the rest of the Hennessy team for today's presentation. I also want to remind everyone that an archive of this webinar will be available through the Modern Tire Dealer website at www.moderntiredealer.com/content/webinars. Thank you, and have a great day.